The best fundamental research has given you lasting, long range, and dramatic dividends. The government is very well intentioned, and I really think that the mood is just right, the attitude is correct, but I think the numbers need to just go up dramatically. We need a large science base in this country.
Namaskar and welcome to another episode of the Professor Mahesh Podcast, your resource to help you make informed career decisions. As we like to think, this is your future simplified. This podcast is brought to you by IIT Madras Global, an initiative of the Office of Global Engagement at IIT Madras. IITM Global is our platform to take everything IIT Madras to the global audience. Come learn more about what their work looks like and what would interest you best in the links in the description below. The topic for today's conversation is physics. Physics is the reason we enjoy all of the engineering that is available to us, that is making our lives so much more comfortable and helping us be so much more efficient than we could be otherwise. Physics and progresses in basic sciences are the reason any country makes strides to become a developed country. To help us understand what are all the exciting prospects in physics and why should a young man or woman today take to physics, I have a fascinating guest, Professor G. Ravindra Kumar from the Tata Institute of Fundamental Research. Professor Ravindra Kumar is an Infosys Laureate and Infosys Prize Laureate and very accomplished experimental physicist. Welcome, Ravi. Thank you very much for making the trek and coming down to Chennai to talk to us.
Well, thank you, Mahesh. Thank you for having me here. And first of all, I'm delighted to know, when I got to know of this initiative, I was very surprised. It looked like that this is something that was really needed to help people make wise decisions about what they're going to do for the rest of their lives. A young person, and I think it's very important in these days of overcrowded information channels and all sorts of opinions being bandied about as the expert advice, to hear somebody who has been through the path to share some of those experiences and then help people decide if they wish to go down the same path and accomplish whatever they want.
Again, thank you for those kind words. Let's start with your own journey. You started out in engineering, but you found your passion very soon in your life, and your calling was physics. Tell us a little bit about maybe your early school teachers, and then your life at BITS that helped you pivot in this direction.
Actually, the Indian society then and even now, it's pretty structured in about how it thinks about various careers. So if you're a boy, you have to be an engineer. If you're a girl, you should aim to be a doctor, or vice versa, depending on which family background you come from. The good thing that happened to me was, of course, there were people in school. Not that education was at a level that was desirable, in the sense in small towns, the schools are pretty low-key about the way they teach. It's all usually rote learning, and then you get a false sense of accomplishment that you're scoring lots of marks and so on. And I guess much of this has remained the same even now. But there were a couple of teachers who used to ask, who made things very interesting. At the so-called intermediate level, at the 10 plus 2, the plus 2 level. So there was a Professor Lakshmi Narayana who used to talk about things like relativity, and at that time, it was so mismatched with the textbook stuff that it looked fascinating to me that he's talking about something which is very exotic. I don't know what it means. But that thing sort of stuck in my mind. And then, there was always, since I used to read a lot, and I used to get, scared that I didn't know many things. Because you read any book with that level of background that we had and with the level of help that we had, it was not much. Those are prehistoric days, if you can call it. There was no internet. There was not even a phone call you could make to somebody to figure out something. So it was mostly a random walk, that you have to do with very little resources. But then the fascination remained. And once I went to BITS, that sort of opened my eyes in the sense that I knew lots of people. They came from all over the country. They knew much more than I did. If you come from Delhi or Bombay or some other place like that, then you had people whose level of education was much better. And in the first year we had courses. We had wonderful courses that time. At that point of time we thought like these courses were not the ones that we had to do. But in hindsight, it turns out that they were really the kind of courses that gave us a background. There was this course called Concepts in Science, which surveyed the whole of science, right, in one semester. And now when I look back at it, and we had cyclostyle notes, the pre-photocopying days, right? So we had cyclostyle fat volume like this, which talked about everything that you could think of in a very nice manner. Elementary, but exposed us to everything. Then the actual physics courses started. And as we started learning more and more, physics, the first 2-3 years, we had this integrated program where we had to do basic courses first. And all of us did that together. So we knew there were lots of people who knew more than us, right? And how come these guys are so smart? They understand all these physics concepts so well. And we have so much to learn. So it was a great peer group. And some of the fascination with physics got further emboldened, further enriched by the books that we had in the library. I don't recall the author, but there was this book called Physics for the Inquiring Mind. It was again a fat book, right? And that literally, the way he talked about stuff, and I didn't even know Feynman lectures in physics at that point of time. But when I knew Feynman lectures in physics, and then, it was clearly no competition for physics, right? And so even though it was, unluckily BITS had this opportunity that, you could do dual degree. So I did a degree in mechanical engineering to satisfy the societal requirements, right? And also the family, sort of ambitions or aspirations. But then I did physics, and then after that, I knew that I wanted to pursue physics. So that was very clear. And the fascination continued when I went to IIT Kanpur, but there was a turn. Because still I was in physics in BITS, but the labs were okay, but not really at the level at which you would expect them to be but the theoretical subjects always had more attention than the experimental stuff. I think it's true of most of India even now. And so when I went to Kanpur, on the other hand, for a PhD, I was asked to do an experimental, I was assigned an advisor who was doing a laser spectroscopy as his research. Yeah. So initially there was a lot of hesitation, and there was a lot of, I'm being very honest, I wanted to be a theorist like all Indian kids trained in physics do, right? But the fact that I had to do that, and suddenly I started meeting people who are really enjoying it, and who are meeting, in those days of very little support in an experimental program. We had labs, research labs were great, but then if something happened to the equipment that you had, there was nobody to come, there was no internet that you could do things on video. So even phone calls were difficult to make in those days. So it turned out that I had some very, very competent seniors, the peers I looked up to at that time and look up to even now. And there was BP Singh, who was 4 years my senior. He became a professor in physics in IIT Bombay. He retired recently. But the way he handled experimental challenges was an eye-opener to me. And it became sort of my own challenge then that, here is somebody who's facing so many problems in the experimental hardware and the experiment, but still, he's just solving one problem after the other. And so I have told him, but not maybe through this podcast, I can tell him again. So he is a great mentor. He's been a great mentor to me since that time. And also another student called Govindarajan, who had a series of failures in his work. He was doing, I think, Rydberg state excitation with a CW dye laser. We don't get into the details now. And these lasers were state of the art, but there was absolutely no support base in the country if anything goes wrong. And even forget about it, even help on the phone was a very difficult thing to reach, right? So we had to learn, we had to think of, what could be happening. Sometimes there were not even circuit drawings to see where the problem was. But these people were just meeting one challenge after the other. So I said, it's possible. Anything is possible in this country. And now Govind happens to be in the ITER project now. He worked in IPR for a long time, then he went to ITER. But they don't know that, I've learned this from them. But I know that I have learned.
Talk of this conundrum between theory and experiment in physics. Yes. The modern view is theoreticians predict and experimentalists follow up later on and quote unquote validate or demonstrate. The Higgs boson is a recent case in point. But that's not the way physics progressed even 300-400 years ago. The famous apple drop and then Einstein's gear started turning, and out comes the theory of gravitation. What is the correct way to think of the view or the balance between theory and experiment?
Okay. So the most generous answer to this would be that it is a science, and science has lots of components. But I believe much of science, there are colleagues who will have a different view, but I believe science has always been observational and about the universe around us. Sure. Right? It's not been an abstract thing that we just think of for the sake of it. We wanted to explain things. In fact, Galileo pointed his telescope to the heavens. And then Kepler's laws came later, right? And then Newton saw something falling, and then the theory of gravitation followed. So, in a manner of speaking, things fall into place when you actually observe and find something that you can't understand and try and make sense of what this is. So, we observe, we sort of, make an experiment, then we make models. From the models, maybe a deeper concept emerges. So I believe this structure has remained the same all through at least the last 400 years.
So this idea that theoreticians sort of precede experimental observations is actually...
there's some truth to it in the sense that, of late in particle physics, for example, high energy particle physics, where you build huge machines. And these are not tabletop experiments that lots of people can do. It's a multinational collaboration where a lot of people have to come together to actually do this, put their money and talents and technical capabilities together to see that an experiment, to search for some prediction. So that's how things have actually got progressed in particle physics in recent times. But earlier, people also discovered in particle physics by sheer observation, much of serendipity, which we don't give credit for, right? Many of the things as late as, a few years ago, Nobel Prizes were given for things which were discovered by serendipity, right? And I would say physics, in my opinion, from my corner, is essentially an experimental science. Because the experimental science can still throw up things that the beautiful theory that you have built up will not reproduce, right? And then you have to further. So I think it's always been a game between theory and experiment. But I believe experiment most of science has preceded theory. Sometimes it can go the other way. And now there are people, some of my colleagues, who pursue theory just for the beauty of the theory. They believe that this theory is so beautiful that, the concepts must be, I'm sure they'll be validated, if not now, in the years to come. Yeah.
Let's switch gears, and we want to talk about careers in physics, and we'll come to that. But before we get there, we want to talk about the different subdisciplines of physics. So let's start with the oldest of them all, in some sense. Let's say dynamics, nonlinear dynamics, or just planetary dynamics, which was the starting point, with Newton's laws, and then that's now practically all gone into the realm of engineering, right? So let's talk of the next level, which is, say, condensed matter physics. right? So, what are the exciting questions in condensed matter physics today?
Well, this would need a very, very long answer. But since time is short, I would say I think the biggest things have been the fact that you have this state of the system. I'm not a condensed matter experimental theorist or an experimentalist, but I'll give my outsider view of it. It's just the fact that, people thought that if you understand the basics of one particle or one fundamental entity, then you'd be able to build on everything as a sum of all the things, lots of particles coming together. But when lots of particles come together, new effects emerge, which is exemplified by condensed matter physics. And not just condensed matter physics, but condensed matter science. Now there are lots of aspects to it. For example, the traditional condensed matter, what's called hard condensed matter, crystals and glasses and so on. And then there's soft condensed matter. And then there is even this exotic subject, which is now becoming very, very common, is called quantum materials, where you really see quantum effects in their full glory, right? Not just in rarefied experiments like where you are trying to observe some correlations or something like that, but in the condensed matter state itself, there's this new phase of quantum materials. There are, I'll just put out a few words: topological insulators, graphene, right? Or there's this various kind of alloys which display very exotic kind of behavior, whether it's transport or optical properties or any other properties, right? And not to talk of the very well known nano, right? Everything is nano these days, right? And if you just look at a part of condensed matter, that is a collection of atoms behaving in response to light. In the optical response itself, there have been fascinating things. There have been quantum wells, which now routinely make lasers. There's meta surfaces, meta materials. All these display. In fact, condensed matter has gone into a realm of where you can make designer materials, I think, in my opinion, and to produce a certain property. And this is a revolution and because condensed matter can be seen, the behavior can be seen in the lab, observed in the lab, the interplay between theory and experiment is so rich. It's one of the most fascinating things. And the last thing, if quantum computers are going to become a commonplace thing, some of the strongest candidates come from condensed matter experiments. Superconducting quantum bits, in which TIFR is doing a lot of work. Sure. And even systems which are somewhat like condensed matter, right? But assemblies of ions and so on and so forth, which may not be actually strictly called condensed matter, but they behave. And in fact, let me also tell you, this soft condensed matter physics, which is supposed to parallel some of the things in biology, is again in for a huge revolution right now, right? So I would say physics has sort of exploded in the last few decades, which is why I believe that any young person should first think of doing physics before anything else, because it's the grandest subject in my opinion, not taking away anything from competing subjects. But from astronomy, the biggest discoveries that we have made in the last few years about gravitational waves and so on, and the varieties of astronomy that have opened up, all the way to the condensed matter, which is again enriching itself in fundamentally different ways, fascinating ways.
So you alluded to astrophysics and cosmology. That's another area where
exactly
there's a lot of excitement happening.
Yeah.
High energy particle physics,
yes.
Our understanding of the atom as it stands, is now probably 50, 60 years old at least, and evolving still.
Yeah.
What are some fundamental questions there that a young man or woman can or should get excited about there?
In which area are you asking?
In high energy particle physics.
High energy particle physics. Again, it's way out of my exposure and experience. I have some I understand a lot of things because my colleagues say that, they explain things to me. But I think high energy has gone into a realm where, it's being done on the Earth in the LHC, and but there's also high energy physics which is happening using other observables, other observatories. And in fact, the earliest experiments done by TIFR were using balloons, which were to look at cosmic rays and so on, which are actually cosmic phenomena. But I believe in the last few years, the observations of these multinational probes, multilateral probes, collaborative probes like that have been launched to look at background, cosmic wave background, and they have put cosmology on a very, very stable sort of platform now, on a foundation. They're putting it better and better. So I think we will understand much deeper. And of course, now you have these gravitational waves which are being observed. I think they're being observed in huge numbers now. After the first discovery was announced in 2016, right? Or 15 or 16, one of these. 100 years after Einstein predicted them. So I think astronomy, and I believe that most areas will not remain isolated. They'll actually start merging with each other, right, with one another. And I think that is the true beauty of science in any case, not just compartmentalizing, but bringing lots of concepts across areas, and also even observations which need multiple disciplines to understand them.
And then there's the early physics, classical physics as it's called, had dynamics and optics. Optics and electromagnetism, which got added on, thanks to Maxwell. That's again the mother of a lot of engineering that we enjoy today. Tell us about where the open questions are in optics and high energy lasers and the work you
That's
do.
very close to my heart. Right? So let me put it this way. In fact, anybody who has done anything in physics, in my opinion, has worked in optics. You take any famous name, because optics was one of those fascinating subjects. For example, Young's double slit experiment, which raised the basic question of, is light a wave or a particle at that time? There were several conflicting things. And that question, the physics world, I think a few years ago, rated this experiment as one of the most beautiful experiments ever done. The Young's double slit. First, it was done with light, and then it was done with particles like electrons. And that set up the whole business of, particles or waves. Do they exist together? How do they manifest? And we've been, thinking about this very actively for the last 60 years after quantum mechanics started. Initially, it was all about setting up quantum mechanics, but I think this understanding foundations of quantum mechanics became very, highly interesting to scientists in the 70s and 80s. And since then, the manifestations of things like entanglement, and now even more because of quantum computing and cryptography and all this. So I think, in my opinion, optics has been one of the biggest drivers of science. And I'm saying it with full consciousness, because if you look at any area of science, whether it is fundamental, like testing quantum mechanics, the Bell's inequalities, that was a laser-driven experiment, right? Gravitational waves needs an interferometer, right? It's a LIGO, right? Or if you look at imaging in biology, condensed matter everywhere, the fact that you can now go and see, things on such a small scale, unheard of, never dreamt before, right, is all because of visualizations in the spatial scale and also on the temporal scale. We are now able to resolve things at the level of attoseconds, right? Which is, if I might say, a thousandth of a femtosecond.
So tell me one thing. I want to interrupt you here. In high school, we are taught of something called the diffraction limit.
Yeah.
What happened to that?
Okay. Well, limits are meant to be broken just as records are, right?
Okay.
So that question has a very layered answer. The answer is that the diffraction limit does not bother us anymore. We have gone highly subdifractive using what is called several techniques. It's called near field imaging, right? Which is always known. This is the beauty of science, that it was always there, but the discovery or the implementation the implementation of this in a certain context takes a long while. Maybe for the technology, maybe you have had to wait for nano probes, micro probes to become available, and so on. But there's no diffraction limits. And in fact, the two limits that still stand are, of course, the speed of light,
Sure.
right, which is a universal thing. And, Planck's constant and several other constants are constants, so they are not to be changed, at least going by existing physics. But I think the diffraction limit was the way of we looked at the phenomenon of diffraction in different zones as light propagates. And that's been beaten in multiple ways using linear techniques, using nonlinear techniques. And so it's been, now you can see at the nanometer level, tens of nanometer level at least, using visible light, which is about a few hundred nanometers. Sure. Right? So I was alluding to something which is even more spectacular or equally spectacular, is this business that, for a long time we had pulses which were the millisecond, microsecond. When lasers came, nanosecond pulses became available in plenty. And the laser, by the way, is one of the greatest inventions of humankind.
It changed everything about...
It is so great that it's become invisible.
Correct.
I'm not talking about invisible lasers, but the laser as a tool is everywhere. We don't even notice it. And that's the greatest thing that you can say about something that is so important in our lives. Like it's almost like breathing.
I think we have to mention Townsend. The man changed everything about us.
And the person who invented the laser is Theodore Maiman, who was at the Hughes Labs. And he was the first one who showed the flash in 1960, May 16th. So that's the birthday of the laser, right? So I think after that, the time, the time durations for which light can be emitted has been now pushed to attoseconds, which I think is again a remarkable achievement. It's happened because of lots of scientific advances, not technology, but you have to understand the science, and then the technology followed, right? So now these days you can get to attoseconds, so you can watch molecules vibrate inside, atoms vibrate inside molecules. You can watch diffract, crystals, the ions moving inside crystals. You can actually see, as people are saying, you can catch the electron cloud changing its shape inside an atom, which happens maybe on the attosecond time scale, right? So to see things as they happen, where they happen, and at the precise detail, how small can you get in space, how small can you get in time, and of course the frequency, if you go to the corresponding limit in frequency, lasers are some of the sharpest frequency devices that you can produce. The LIGO, the laser that was used in LIGO, has line widths that you can't even imagine. They're so small, and that's why they have this long coherence length, which makes this interferometer work so beautifully. And in fact, if you ask me, the greatest achievement of humankind across all areas has been the discovery of gravitational waves. Simply because the way they push the technology, the way they push the limits of sensitivity, precision, and they continue to push that. There are several competitors, again, driven by lasers. For example, you can talk about the fusion experiment that's on in the US for a long time at the Livermore Labs, which had a breakthrough a few years ago. And so these are all things that are not possible without first-rate fundamental science pushed for decades together, right? And these happen to be across now. In a way, I think we are not restricting, all these, the science itself is not compartmentalized. You need concepts from that other people know, because each subject has developed so deeply that nobody can understand across areas. So you bring in experts, scientists from all over the world,
including engineers now.
Engineers, and I must say that, I'm talking to an engineer, and I must say, engineering has driven science. For example, the LIGO or the LHC or the ITER experiment, the International Thermonuclear Experimental Reactor in Cadarache in France, is a marvel of engineering. And so engineering pushes science. And science then spins into technology and engineering. And this is a cycle that just should go on.
Correct. We'll come to that cycle. Yeah. But let's talk of the last and the most recent probably addition to the subdisciplines of physics, quantum mechanics. Yeah. We are in the 100th year of the discovery or the proposal of quantum
1925 to 2025. Yes, you're right.
In 100 years, it's come from a theory that a handful of people understood to where we now have regular people in a society talk of some benefits they can derive. There's probably no scientific discipline that has gone so fast into popular lexicon So tell us a
Yes.
little bit about where the prospects are. What is it that we can see happen due to directly due to quantum mechanics? I mean, we all know that satellites are able to communicate largely due to quantum mechanical effects, and there are other areas where quantum mechanics has already made a difference. But more tangibly, more specifically, what are the high level
To take
benefits?
you off from what you said initially, from a subject that everybody said only he understands or she understands, right? I don't understand, go and ask him. To something which has become so common. I mean, it's an astonishing journey. In fact, if you ask me, quantum mechanics is everywhere because it's the way we understand matter and interactions, right? So, quantum mechanics is a refinement of all the things that we knew so far at that time. Classical physics became understood in quantum mechanical terms. So, quantum mechanics is everywhere. A big body like you and me can also be explained by quantum mechanics. Maybe it's not needed because there are simpler ways of understanding it. So, quantum mechanics is everywhere because it's a part of nature, right? The way we understand nature is through quantum mechanics. But of late, the manifestations that became very obvious are because of the fact that, several fundamental concepts, this belief that, this proposal that quantum behavior is inherently different from classical behavior. Quantization can also exist in classical physics. I mean, you have boundary conditions that leads to quantization. But this business of entanglement, the fact that there's information that is coded in a particle and the particle subdivides, and the information on one can be known by making measurements on the other. It's a fascinating concept. And this is the reason why entanglement has driven, as I said, as a fundamental concept, and also in condensed matter now, and even in, I think, I may be wrong, but I hear even people talking about entangled on a large scale in the universe, right? Things are entangled. So some concepts have become so common because this is a fascinating concept. And the reason I think this entanglement is something that is going to, I mean, it's very enriching, very difficult to grasp for a common person. But this is the heart of lots of quantum things that we do, whether it's computing or cryptography, conveying information to information processing and so on. So you can have a quantum key. Again, my knowledge is very peripheral. So quantum keys that will make sure that nobody else can eavesdrop. And lots of work going on at TIFR, even in this and elsewhere in the country. And now even I believe the defense establishments are interested in this. So, for example, much of the big things that we see, satellites being launched, they can all be beautifully, you see the trajectory when ISRO launches a satellite. And I used to see with fascination, the curve exactly goes like what we predicted on the screen. And then there's a huge amount of applause when scientists are elated that it has been placed in the orbit. So much of that is classical physics. And you don't need quantum mechanics to describe such a huge object. But quantum mechanics works for you, whether it's huge or small. But in the micro and nano and pico realms, you need quantum mechanics to predict the correct behavior, right? Even if you don't understand all the implications, you use the correct quantum tools and you get the correct physics. And that's been proved again and again in the last several decades.
Just as a little aside, I was talking to another person on this podcast earlier who said they're beginning to discover quantum effects in the human body at human body temperatures. Yeah. So, which is in itself it's a mind-boggling thing. And then increasingly there are now these sort of non-standard disciplines. We hear medical physics. Right, the word physics has now become associated with the world of medicine in some way. Again, optics and imaging is central to that whole world of medical physics. So help us understand some exciting questions in the field of medicine married to physics.
Okay, so if you say that, of course, the moment cells were seen under a microscope, maybe that was the beginning of medical physics, if you ask me. That way it was optics. But now it has become like, since I said, I don't think you can quantify this as this thing has helped medicine or medical physics, therapies. There are all the things from looking at abnormal cells under a microscope or normal cells under a microscope to making several uh, discoveries about what's in your blood, doing fluorescence analysis, right? Or using optical techniques, whatever techniques you can think of, to where it is coming. Uh, Imaging has been pushed to a great level, but now there are several tools that you can use to actually attack in my area, what I work on, high energy density science. One of the things that comes is that the lasers drive particles, which are very high energy, and these particles come as bunches, and these bunches can actually kill cancer cells locally. And I think that's a very beautiful way of using this. Nobody thought of this, like in the sense that people said, okay, highly charged particle beams can penetrate and kill tissue, which is dirty, which is dangerous to the human body. But now the fact that it's always been not on an accelerator but driven by a laser system, which is on a much smaller scale. So I think medical physics used to be, if you ask a radiologist, he will say, oh, because I'm using X-ray, right, to diagnose or to kill something or to kill malignant cells or to do something else, to do tomography, right? Or if you ask even NMR is actually physics, right? It's chemistry also, but physics nevertheless, right? Spins. So I think it's very difficult. It's like, you can't, it's like such a universal thing now that you can't say this is this and that is that. I mean, it's there cloaked in different forms. It appears different to you. So it's different manifestations, but the underlying is all the basic concepts of physics. Yeah.
Let's step back. And there are all these subdisciplines of physics, and you've already made the point that these subdisciplines are increasingly finding common ground. Yeah. They're not like hard subdisciplines any longer. But for a physicist, a young physicist or an aspirational physicist, okay, there are a lot of opportunities out there. So I want to address 2 or 3 challenges that I sort of perceive from the students who want to pursue physics. One, it takes a long time to jump into the center or to the core of an exciting question. Is that in any way true?
Depends. I think it has to do with your preparation. And if it's an Indian context, I have lots of things to say. I think we need a dramatic reform in the way we teach science. There may be some partial efforts here and there localized, but I believe much of our learning is still old-fashioned, rote learning. We never teach a student how to think about science or how to, to learn. We never teach them how to learn. We are completing syllabus. One of my favorite ways of saying this to a teacher, I'm sorry, is that, people say, have you covered the syllabus? So my standard answer to this, I don't want to cover anything. I want to uncover a few basic things, right? So that the student appreciates them. Because you can't teach a person everything, but you have to teach them how to think. And this being said in glorious style by the, Richard Feynman, when he said, you need to get to the crux of the matter, think about the basics and think about them again and again in different ways and see them manifest, internalize them. Then you can use it. So I would not say that, it's very difficult to get into an area. There's enough help. There's more help than ever in understanding something. But there are some subjects which are always, they take a long, preparation period. Some of the theoretical subjects which are at an advanced level. If you wish to do the greatest experiment, of course you have to learn the skills. But the beauty of physics and much of science, except probably biology, for example, which is multi-layered and it is quite complex that way, is that there are a few basic things that you need to learn, and the few basic things will stay with you all through your life. Okay. Right? So if it's an experiment, the measurables, the techniques are pretty much the way you start thinking about techniques is common between me as a condensed matter, among all of us as an optics guy, as a laser guy, a condensed matter person, an astronomer. We basically ask same kind of questions, use similar kind of tools. The observables are very, very similar. They may give them a different name. I may give them a different name. But there's not really too much of basic learning that you have to do to enter. But if you want to go to the advanced level, And by the way, what do you define as an advanced level is because to me, questions occur at different layers again, right? So a good student, I've been surprised by a student in my lab who enters with very little background in experimental science. And ours is a highly sophisticated experimental lab dealing with hundreds of terawatt, femtosecond lasers. But I'm astonished. This student who knows nothing about all this can pick up things. They're bright, admittedly, but they can pick up things in just a few months. And it's a question, it's a way of how you talk to them. I think much of the challenge is for the teacher to say, how do you pose a question? And how do you make the student pose the question? How do you get him to align with the way of the way the field thinks, the way the practitioners think? So admittedly, there are few areas where you need a lot of, to do a LIGO experiment, you not only need huge skills, you need number of people with different skills, but we are not aiming at that. We are talking about enjoying yourself while you're getting trained. And that is not so difficult to do.
The second misconception is that the mathematics bar, or the training in formal mathematics to really do good physics has gone to become quite high. Is that a misconception, or is there some
I would
truth
think so.
to it?
Because I should say that I'm not, I don't claim that I have great ability in maths, to be honest. But we all have a reasonable ability. It depends on what you want to do. Suppose you have to learn something, you spend a lot of time. Then you may not be the greatest guy in that field, but you acquire enough competence in that area to make progress, right? But it is not true. And I would like to tell people that these misconceptions, as you correctly call them, these phobias that people build, right? And I'm in an IIT where, of course, everyone is gifted. We're not talking about different kind of crowd here. But even to the average person in a small town, and I've been taken aback by, when I observe some of these people who come from small towns to TIFR, that these are people who have had, some of them were privileged. They went to presidency and, in places like that in West Bengal. But there are people who come from Haryana, who come from Rajasthan, who have had modest education, but their internal innate ability is, of course, very good, but very quickly they pick up. And there are ways of, these days with all the internet resources, which are sort of spoon feeding you in more ways than one, it's very easy to learn all the skills and techniques that you need. So I would like young people to think that nothing is difficult. In 2025, nothing is difficult if you want to learn.
Okay.
Right?
Good. Good. I think that's an important lesson, important takeaway point for the audience. Let's talk about what this whole world of artificial intelligence is doing.
Okay.
As we know, last year's Physics Nobel Prize went for the invention of the Hopfield network, which was the fundamental building block of what we today know as deep learning algorithms.
Yeah.
Where is AI interfacing with physics, or what is some tangible benefits you think we can see there?
Yeah, so it's again an exploding area. So I think anything that we say will probably be proved wrong or will be very soon outdated. So there's just no point in saying it. But I think the point is that AI is throwing up opportunities. Let me begin in a different way. Let me say in experimental science, which is what is my forte. For a long time, we have been trying to, begin with an example. We've been trying to focus the laser beam, which is amplified laser beam with lots of aberrations on it. And now we borrow techniques from astronomy, which is called adaptive optics. So you have this deformable mirror, which is adjusts the wavefront so that you can get it to near the diffraction limit, as close to the diffraction limit as possible. And so this deformable mirror has multiple actuators, right? Now these multiple actuators have to be fired so that the phase at that point in space is correctly adjusted to produce the sharpest point,
Sure.
Right? So to make it as plain wave as possible in a manner of speaking, right? So 20 years ago, we asked this question when we bought the first deformable mirror, that why can't we just have something which is just pushing it rather than, go by some known algorithm which gives you some predicted value, but not the best value. But suppose I give you all options to push every knob, every little actuator there on the mirror, and then maybe it can do all permutations and combinations and give me the correct result. So this was 20 years ago when we were grappling with this problem. Now that looks like something which artificial intelligence can easily do. We
Right.
put all sorts of wavefronts, feed them, and tell the actuators to go berserk, right?
Yeah.
And it will come to the correct thing. Yeah. So one of my colleagues, who is an astrophysicist, he works on helioseismology. He was just looking at lots of data, observations made by satellites over the years, and trying to see something about the behavior of these stars. And he said, suddenly I put in all this data and ran this deep learning algorithm. Now it's giving me all these predictions, which normally if we had to do a formal manual search or a intelligent search, we wouldn't have been able to get. It would have taken us years and years of effort, right? So I think data-wise, we have huge amounts of data, which is coming up from various observational sources, particularly in areas like astronomy, particle physics, and even, all of us are sharing data now across small fields of science. So, and biology is again a major revelation, because again, I'll give you an example of what TIFR is involved in. We have this Extreme Photonics Innovation Center in collaboration with the UKRI, and our collaborator in the UK is the Rutherford Appleton Labs, the Science and Technology Facilities Council. They started a project with us in optics, for the next generation of lasers and so on and so forth. It's an entity located in TIFR Hyderabad with the UK funding, right? They enlarged this to include a bioimaging initiative in the last couple of years, simply because India has such rich data on cancer, right? The Tata Memorial Hospital, which is again a part of the Department of Atomic Energy, to which I belong. They have huge amount of data collected over the last 30, 40 years of cancer patients. So they look at this cancerous tissue, predict what kind of tissue are likely to evolve into a cancerous stage, very early on. And that I think is going to be a huge, benefit for cancer, predicting cancer and curing cancer well before it becomes unmanageable. So data-wise, I think scientific data are as good as any to benefit from artificial intelligence. But from an experimental perspective, I believe that I wonder someday that, the laser has so many controls. Why doesn't an AM machine just do this and give me the best possible beam? I'm sure one of these days it will happen. So I think if we intelligently use AI even in the hardware, which is already happening, right? I think we'll be able to make huge strides in basic science and also technology.
You had earlier alluded to engineering helping the progression of science, and science contributing to new engineering and technology, that virtuous cycle. AI is very much a central piece in that whole, in that network of, one feeding into each other. Let's step back and talk about physics in India. Right? We have a massive, I don't know the numbers. I know the numbers in India, but I don't know where we stand vis-a-vis the rest of the world. But we probably have the largest contingent of physics studying students of probably any country in the world. I mean, one of the largest for sure. Right? Where do you see potential careers for them? Let's. I think we have to take this problem head on, right? The obvious careers are in academia and research, but are there other new avenues that seem to be emerging on the fringes of physics, of the core physics, where students can find gainful employment, contribute positively, and also alongside make a good living?
So, firstly, even in academics, though, let's dispose of that first. I think the opportunities are tremendous, right? But let's move away. I will not talk about, let's talk about some non-traditional areas. Physics has always driven industry and technology, particularly if you look at in the West, in the normal technology domain and also in the strategic domain. Bell Labs was full of physicists, right? IBM invested hugely in physics. The semiconductor manufacturing was all driven by physicists.
Wall Street
Wall Street is also driven by physicists. right? Making models for how things might emerge in the stock market,
Sure.
right? The point I think is physics is such a general science, and in India our perspective was very limited because of the way we were in the 70s and 80s and 90s. I dare say even in the early 2000s. But India today is very different, right? We don't. I think from our restricted viewpoint that we used to see that India to do things in India for Indians, and that is such a small pie that it doesn't look attractive at all. But since our IT guys have started going all over the world, and they're helping everyone in the world, solve their problems in whatever way they can. I think now India is science also, physics also should be seen in a globalized context. A good physics degree opens you to lots and lots of opportunities in, if you don't like doing academics, by far, that's fine, right? Industry, like the West, if you believe that India has a demographic advantage right now, and everybody else, the populations are shrinking. I think Indian faces will be needed all over the world, right? We don't think of living in India and staying in India, doing things in India all the time. It could be, we can be partially migratory, returning to India, and the Indian scene itself is also changing. Now, I think we're at a stage where we have perhaps overcome our earlier hesitations and perceived limitations. Most of them were mental. And also some of them were situational, economical, because we were at a stage where we are not rich
Do
enough.
you see the early foresight of a Bell Labs-like establishment sprouting out of an
I
Indian?
think I wish it happens, but in a different way. I don't know what form it might take, but there is a message when I said Bell Labs, right? Bell Labs was supposed to be a communication company, but go and see how many Nobel Prizes for physics they won.
Yeah.
The laser cooling Nobel Prize went to Steve Chu,
Yeah.
who did that in Bell Labs. Arthur Ashkin, the tweezers guy.
And the company profited from these discoveries.
Exactly.
It's not like...
Exactly. The IBM discovered, if I'm not wrong, the electron microscopies, the CCDs, and all these things. And Hughes Labs made discoveries of the laser, right? And similarly, if you look at it, I think I'm hoping that there will be something like a phase transition, to use a word from physics, in the way the society sees science and the government sees science. So the government is understandably very concerned about the science population. And if you look for temporary solutions like, how to solve problems for this particular 5-year period, we may not go far. The reason I'm saying that investments made now in science, education in science, and in science research, by 2047, you will reap huge dividends. But we need persistence, we need continuous kind of attention there, and we need funding, sustained funding at a level which is much higher than right now. But if you go back to careers, right, I would say I do see industries opening up here, and I was very pleasantly surprised. There are so many startups manufacturing things in India, and you have the Techno Park here. I'm very excited about Research Park. And in Hyderabad and Bangalore, there's this ecosystem which is developing so rapidly for making things, hard manufacturing, which need a lot of physics. There are people making satellites, right? They need engineers, but physicists can also be engineers.
Sure. Sure. I think they can contribute in a very positive way.
Very positive way. And I think they'll make a lot of money, because I think the young people, one thing that really encourages me is the young people have no hesitations of the past. And they're not bothered by the way we are beating everyone in cricket.
Yep.
Right? We can beat anybody in anything if you give these young people a chance and the right encouragement.
So you talked of investments in science research. As a country, we now have the ANRF, which is taken off in a nice way, and their mandate is to bring together an army of science thinking researchers, students, and researcher professors, and create a soup for future engineering to be done in India.
Yes.
That's roughly the mandate, and in that mix, like the confidence that today's generation brings to the table is absolutely the foundation on which these programs are built. In institutions like TIFR or at IISc or in the IITs, what are the systemic changes that we need to bring to really make sure that the science is done focused towards tomorrow's engineering? Or is that not at all the right way to think?
Okay. So you're talking to a fundamental researcher.
Yes, that's the reason I brought
come
this
from
up.
Tata Institute of Fundamental Research. I believe that this division of fundamental versus applied is, in my opinion, somewhat artificial, because I think going by the examples that we have talked about till now, the best fundamental research has given you lasting, long range, and dramatic dividends.
There is no argument at all.
There is no argument at all.
Yes.
So my point is, the government is very well intentioned, and I really think that everything, the mood is just right, the attitude is correct, but I think the numbers need to just go up dramatically. We need a large science base in this country, and that will of course provide more employment to young
I
people.
want to argue for just a moment to provide, just to sort of discuss a counterpoint there. Science does not respect geographical borders.
Sure.
Science done in the US benefits industry in India.
Yeah.
So why should the government of India
Yeah.
invest in research to be done in India when I can benefit just as well from science being done elsewhere?
Well, okay, my short answer to that is, if you want to be a world leader, you cannot be looking to somebody else to generate knowledge. You need to have knowledge that nobody has discovered before. You need to be able to command the entire, make sure that the entire world sees you as a source of knowledge that you have first priority on using, right? So we've always been borrowing. Of course, science is universal. We learn from anywhere, anybody does anything, any fundamental discovery is everybody's science after that. But the point is, the guy who makes the discovery, the person who makes the discovery, knows what went into making the discovery, has first access to it, can internalize it much faster than anybody else. There could be some exceptions, but then the point is that, and for a nation to have confidence, I think one of the fundamental things is to generate knowledge. Yeah. And right from, our evolution, I mean, if you look at only India's evolution down the years, we've always believed in that, we create knowledge by thinking about it, by doing, by observing, and we had great astronomers, by the way, that we don't talk of, way back, hundreds and hundreds of years before, right? So Aryabhatta and people like that, on whom the first satellite was named by ISRO. So I think we had people who were interested in the universe, and that tradition should continue. But modern science is very different. Modern science is universal. I mean, it's practiced by many, many more people than even in, when quantum mechanics was discovered. There were not so many scientists across the world. But now there are millions of scientists across the world, and some of them have an applied goal in mind, some of them have a pure science goal in mind, but all of them, you have to compete with this entire pool of people, the large pool, the ever-expanding pool. And I think you have to stand on your own legs. There are no two ways about it. You can't live on borrowed knowledge. You can't also be seen to be aping somebody. He made this device, I made this better, or I made this. I am really looking forward to the day when a new paradigm comes from India. Well, we haven't done it so far. All of us probably take the blame for it.
But I think the situation is ripe for,
it's ripe
for all
and
of that.
Allow me to just say a few more things. I am actually pitching for the positive momentum that's been created should be, given a huge, lift up right now. And we need to increase the funding substantially. The government should still remain for at least some more time the biggest funder of basic science without, looking for maybe immediate benefits. The benefits will come, going by the history of science. The benefits will come, and they'll come in spectacular fashion, and they'll be yours, right? So I'm pitching for ours. They'll be the countries, and they'll be the globe, everybody on the. I mean, if India has to be a leader, and I do foresee that India wants to be a leader by 2047, and that year, I think we should really see India as among the top nations in science. That will not happen unless you expand the base of science and you increase funding regularly over the next 10, 15 years, and to a level, and give scientists enough freedom to think about what they are doing, to encourage. There will always be some, people who will not succeed. The typical success rate is about maybe 10%, 20%, but that will not happen unless you create a large base and see substantial number of people coming up. And so sustained funding, increased funding over a long time. And I think this science will not be just science anymore. There'll be benefits on the way. But I'm talking about spectacular advances will take time to come. And while we are learning from everyone, implementing in our own way what we are learning from the world, we should be leaders in generation of knowledge in the scientific domain. And I pitch for dramatically increased funding. Right? I pitch for the private sector to come in greatly, but I think that for the next near future, I think the government should increase the funding dramatically, which is what the NRF is trying to do. But they should do much more. And I'll give you a comparison. China, we always keep talking about China, but China should be an inspiring role model here, right? Not to be seen as can be seen as a competitor, but an inspiring role model in this aspect of science funding. In 2015, the numbers were that China spent 30 times more than India, right? And India has not caught up. China is spending even more now. And some of the biggest multinational companies, like in software, like Alphabet, spend more than what India spent. One company spent more than what India spent. So as the Indian economy grows more and more, the percentage will certainly yield more money to the scientists. But I'm talking about increasing the percentage itself, which is what the NRF has been trying to do. That, to increase the percentage even fund.
I think this is nicely framed the whole situation for science pursuing students in India, particularly physics pursuing. Your closing thoughts, Ravi, and I think there is a lot clearly for a young student to come in and contribute and make a living. Your closing thoughts on that.
So my closing thoughts, I never got to talk about my own area of research in all this conversation. So I would say that, I'll pitch for experimental physics, experimental science in general. I think India has to increase dramatically the attention it gives to experimental science, starting from the school level and sustained throughout. Physics or science remains a blackboard activity or a PowerPoint activity will not take us far. In fact, all the things that I said about encouraging people to get into creating new knowledge and so on, if you look at history of humankind, people have always, created things with their hands, created structures, created and observed things, made use of them. And if we are just conceptualizing without actually doing experimental science, and we are using data from somewhere else, not creating it here, I think we'll not go far. So my recommendation, the strongest recommendation, is that we should change the education system in such a way that it becomes much more experimental right from the school level. Of course, this needs huge amount of attention from the government and also the whatever philanthropic agencies we have, and make it an activity that people enjoy doing. You asked a question, if you ask me, most Indian students want to do theory. Why? Because that's all that they have learned. They have never really seen a fascinating experiment in action, right? They have never really observed the things around them, right? And most of them know theoretical concepts. They can't explain why a leaf is green, why the sky is blue, right? Why there are waves not just on the sea, but also in the desert, right? They don't know anything. And your own area of fluid mechanics, for example, there are lots of things that you can observe by just watching fluids.
Yes.
How much of that, they would rather write a differential equation to understand that rather than observe and see. And let me also tell you, some of the new things that I have learned quite away from my area is about how when a droplet falls, what kind of a shape it takes on when it touches the surface. And that was done by high-speed microscopy. So go back again to what we talked till now, in the sense that everything is fitting into everything else, but observe, experiment, and learn and enjoy. I think all these phobias will disappear when you make sense of something that you're watching, that you're observing. And we have to change our education system to open the kids' minds, fascinate them with things which are day-to-day things. And it doesn't have to be an esoteric activity confined to a science camp or a public lecture by, open day of IIT Madras, where people come and watch fancy experiments, but they can't make sense. They're just fascinated, but they don't know how to understand because their eye has not been opened up. And somebody who walks into my laser lab, planning to do theory, easily converted to doing a laser experiment because he sees such fascinating way the light, intense light interacts with matter and creates stars on the earth, right? So this is what I call Tare Zameen Par. So that's what we do. We create interstellar conditions or mimic them on a tabletop. And why would you not be interested? Of course you would be. And this is not just experiment. It needs very sophisticated computer science, computer modeling. It needs a lot of plasma physics theory to understand. And it is absolutely first rate. So I would pitch for lots of Indian students doing experimental science, engineering. Again, engineering should not be theoretical, as most Indian engineers tend to do, but it should be build things, surprise the world with something that you have built here, totally new idea, a new concept. So make things more experimental, more experiential, and also change the way people think about the world around us, right? Yeah.
That's a wonderful closing thought that I think we in India need to not be afraid of getting our hands dirty, get into a lab, experience failure. It's hard to experience failure in a theoretical environment as much as you can experience failure in a lab, right? And I think it's very important that we learn through that adversity, and there's no substitute to that. I think we sometimes tend to run away from things like that in India. But thank you for summing up those last thoughts, and thank you for coming, and thank you for sharing.
I might just add one thing. The notion that we get hands dirty. For example, when we create a piece of art, we do it with your fingers. You're not making your hands dirty. You're creating a beautiful thing.
Correct.
So experiments are also beautiful. So there's this notion that it's somehow less of a task than thinking with your brain. But an experimental scientist needs to know great concepts, great theoretical knowledge, great skills to imagine experiments, what can be done, what is observable, what is not, and also think of a way of realizing what he wants to do or she wants to do, and making sense of everything that is thrown by the experiment at you, right? So he or she has to be an all-round scientist, not just, and of course there are soft skills that you can't ignore. How to work in a collaboration.
Sure.
How to learn things from other people, which kind of skills you want. And the greatest thing is to see evolve, questions as you move along, as the challenges get thrown up, as you very rightly said.
Sure.
So persistence and tenacity, right? And great imagination. Yeah.
Sure. Thank you again very much, Ravi. This has been another episode of the Professor Mahesh Podcast. We had an opportunity today to dive into the whole exciting world of physics and all of the potential discoveries that are waiting to be made by young men and women who are physics students in India today. Thank you all for listening. This podcast is brought to you by IITM Global. Learn more about their activities in the link in the description below. Until we meet again, be well, do good, and keep in touch.